Here it is. Right, so our talk. Welcome to our talk. It's mostly about modern application modernization. And we both, Mary and I, are a big fan of reactive, the reactive approach. Um, Reactive can be a bit confusing. Of course, everybody knows it can be reactive programming, but it also can be reactive systems in the sense of systems that are scalable, resilient, and the reactive manifesto and all of that. We're not going to introduce that, but what we're going to show is a simple but effective way, sort of a pragmatic way to modernize your existing, maybe older application that is maybe it's a monolith that you want to break down. It's an older functioning application that maybe is a little bit slowing down and unable to scale. And so we're going to venture into this topic, and we are going to start with a quick demo that you can find on GitHub. What you're seeing is the GitHub page of the demo, and there's mainly 4 little projects in this repository. The infra project really just contains a Docker Compose file to spin up some infrastructure that we need, such as Kafka, which we'll be using for as a source and final destination of our processed data. We'll be basically reading, as you can see in this picture down here, we will be reading messages from a Kafka topic into our legacy processor number 1, and then pass some process data onto the legacy processor number 2. And then finally, the outcome of the processing of this entire flow will be put onto a new Kafka topic. Sources producer, this little project here, is it's really just a little program that puts messages on the first Kafka topic so that they can be consumed by the other 2 legacy processors. And what we are going to focus on specifically is that this entire flow from source to sink is entirely back pressured. Back pressure, as Mary will explain later in more of a bit of a slide section of our talk, is a way to protect your services from being overloaded. So in short, if you have a slower consumer, back pressure is this mechanism according to which the slower consumer, in this case legacy processor 2, can tell to the first legacy processor, or in general to the upstream source of data, to please slow down because I can't keep up. You're overloading me with data, so please slow down. This is, in essence, what back pressure is. And in order to implement back pressure, we need protocols that support it. So between these 2 legacy processors, we are using a relatively new protocol called RSocket, this one here. RSocket is, in short, a application layer protocol. If you want, it's a competitor of HTTP, which allows sending data in a fully controlled way between 2 different services. So it's an end-to-end, point-to-point communication protocol that has back pressure built in. So it puts the receiver in control from the start. All right, with this setup introduced, let's see how this can work in practice. So we are in our infra folder, and we are going to just spin up our infrastructure. As you can see, in this folder, there's only a Docker Compose file, which we spin up by saying Docker Compose up. So what this is doing is creating a Kafka, a Kafka broker that will just sit there and wait. Now, what we are going to do next in another terminal is start putting some data into our Kafka topic. And so this is just a JVM app starting up. And if everything goes right, we should see some messages. Yeah, there you go. So it's creating one message per second, and it's putting it on the topic with a little bit of a timestamp right there. Okay, perfect. So now that there is some data to consume on the topic, let's start our two legacy producer. Actually, let me make this windows a little bit bigger because we know what's happening in the windows on top. There we go. We are going to start the legacy processor number one. This is a Scala app. So something else very interesting that we're looking at here is that we're going to have one Scala app and one Java app. So we'll see how our socket can be used, of course, just like any other communication protocol between different processes on different runtimes and whatever. So okay, there is something interesting already to see. This Kafka topic is full of data by now, but the processor one, the first processor, is not doing anything. And why is that? Because the second processor hasn't yet started. That means that because we have back pressure built in, there is no demand from downstream. And so the legacy processor one is just not doing anything because nobody has requested any data. So let's start now the the legacy processor two. Now, with this process starting, they are going to find each other. Takes a little bit. But when they find each other, you will see that the first legacy processor will start consuming data from Kafka. Interesting. They usually find each other quicker. Maybe the second processor wants more space. There you go. Here it is. So maybe the second processor really wanted more screen estate to be found. Okay, so let's look a little bit at what's happening. The second legacy processor is taken for each item that it receives different times to process it. And so when it takes only 1 second, as you can see, the first legacy processor immediately grabs another message from the Kafka topic and passes it down to the second legacy processor. But every now and then, the second legacy processor takes longer, 5 seconds, to process one message. And while these 5 seconds are elapsing, see now, the first legacy processor doesn't move. So this is our confirmation that this flow is entirely back pressured. As soon as the demand ceases from downstream, nothing happens upstream. The first legacy processor completely stops. See, right now, the second one's processing, the first one does nothing. And so we believe, so this is all for the demo, really. We believe that this way, having back pressure end-to-end is a way to protect your legacy services from higher loads. And in the end, what you can do is you can just quickly encapsulate them into this back pressure enabled communication protocol. And you know that from the start they are protected. You don't need to worry too much about testing it and whatnot and be afraid of failure because they can't be overloaded. Well, that was the quick demo. You are totally welcome to get the repository. It will be shared later. Now I just want to maybe show you the code just very quickly before I pass the microphone to Mary. The legacy processor 1 is basically one single file. It relies on akka streams, which is akka is this toolkit to build distributed systems, and akka streams is the section of akka that provides streaming logic. So streaming in the sense that you will have this basically this pipeline here that we have built within this process is consuming, it's starting to consume from a Kafka subscription, then processing these items. Each item will be executed, in this function down here. It really doesn't do much at this point. And then it will push all the item down the RSocket sink. And this is all we need. Akka Stream really provides this streaming semantics that are really, really powerful. And the RSocket sink is a component, it's just a component that allows you to communicate via WebSocket. So now in this case, if we want to look at this code a little bit, I am specifying a host, local host, because I'm running everything local. And then, well, this is a little bit akka streams syntax and logic, but in general, what you can see, everything is commented here. So if you want to look at the code and learn how it works, in general, what you will have is that only when the consumer downstream will request a new item, so we are roughly in this block here, only then we are going to send one item downstream with this logic here. So yeah, this is basically for the first legacy processor, while the second legacy processor, which is in turn a Java app, it's a little bit longer. It first basically creates a RSocket server that accepts incoming connection from the legacy processor 1, specifying that we're using TCP, binding in this port and things like that. And basically what you see here is the logic that defines what to do when we receive a payload. And well, all that we are doing really is doing some other processing, some fake processing that takes either 1 or 5 seconds, and then publishing the result onto the destination Kafka topic. And what is crucial here is that when we return, when this entire body returns, in this case, in this line, this is where we signal to the producer upstreams that we are ready to process the next item. So before this method has finished executing, the producer upstreams is not allowed to send a new item down the stream. And so you are very, very welcome to check this process and this project online. Please ask me any question necessary that you might have. And with this, I am passing the screen and the microphone to my co-speaker, Mary.
Thank you, Fabio. Thank you. Yeah, so I'll share my screen now. Okay, so everybody can see my slides. Yeah. Okay. Oh, actually, I need to play. So okay. So okay. So everybody, welcome. And my name is Mary Grygleski, and thank you to Eric who has already introduced me and also introduced Fabio too. So just excuse me a second. I may be coughing a little bit because I came down with not COVID. Thankfully, just a regular flu. So and I may be kind of now going back to the the reasoning behind our talk, and essentially we want to talk about how do we retrofit a legacy Java app, and that's we went straight, and Fabio went straight to the demo part, just illustrating how do you build a reactive pipeline. So using Akka, and also then leveraging on Kafka to do the pipelining thing. So now let's kind of go back to a bit kind of describing the rationale behind it. So yeah, so as such too, we already have done, the original agenda is having an introduction and then talking about some history behind, the JVM application enterprise level, and also a lot more complex problems has cropped up. So, so how do we deal with it? So that's when we propose using a reactive approach to doing like solutioning part, and already Fabio has done the part 4 and 5, solutioning and a reactive flow pipeline use case scenario. So, okay, introduction, I'll skip. Well, thank you again for Eric introducing us. So let's kind of go back a little bit. In traditional enterprise JVM apps, especially, most of the time too, we hear about monoliths, right? We have like maybe one JVM, and then inside we're like running many different components. And then, as a result too, yeah, the communication part is a lot easier. You don't have to deal a lot more with the networking side of things. But the thing is too, is that that this kind of approach will require a lot of heavier duty, like operational teams to help with deploying. If you want to make changes to one component, let's say a complex e-commerce system, then you just want to make changes to an ordering subcomponent, then essentially you have to bring down the whole system and then install your new things or replace that part and then build and test. And as you can see, it's kind of not very practical, especially in today's world when everything we're working with a cloud and cloud native. So it really incurs a huge maintenance cost, and a lot of also challenges too. And how do you deal with like concurrent processing, things like that? So so that's when we kind of came up. Fabio and I came together and then talk about how can we solve this problem. So we kind of, this talk too essentially is a bit more of an kind of suggestion, a kind of inspirational, I suppose, to give you some idea. So Fabio already demonstrate, like, what if we take a legacy application that used to be monolith, and then you identify the flow of a certain workflow, and then you essentially to retrofit it and redesign just that part of dealing with the data coming in, and how do you kind of make it flow through different system. And the nice thing too about reactive systems is the back pressure control. And that's when, the software, if you have, we're kind of looking at data, we'll look at it. So then there's the producer part and also the consumer side. So we want to also control, because what if, an application such as an IoT, you install many devices up on a big farm field, and you can be collecting the water or some kind of measurement of the, the environment. So you're sending a lot of data at the same time to hundreds of, from hundreds of devices up to your server. So you want to be able to make sure that the data coming in is not going to, so to speak, like choke your processor. You have producer coming in and there are consumer waiting, but you don't want to choke it. So there's the nice thing about using reactive streams is that it will have the mechanism of controlling the back pressure that otherwise would kind of build up, right? And it's essentially too, you don't want data to be on the producer side to be overwhelming your consuming side. So anyway, so that's the thing about the back pressure part. Then, and then also too, we are also dealing with, not just that, there are many complex problems, that crop up in, this new kind of cloud native world. We're dealing with containers and everything, really everything is distributed in many ways, and transactions and all of these things, dealing with concurrency, the asynchronous nature that will event driven, that will actually, kind of require us to seek new solution, new ways of doing things to handle the data, the amount of data. So now then, we're kind of looking into solutions using the reactive approach. And these days too, with cloud native, it's all about microservices because it really encapsulates your logic very well. And you isolate all of your resources is also wrapped within the microservices. Although it may not be perfect, but that's actually the theoretical side. Microservices, you have all of your resources and they kind of work in a shared kind of mechanism too. So yeah, I just want to make sure I'm not running out of time. So, okay. And so now too is that, with reactive approach, there's also DevOps too, versus the traditional operations that I kind of brought up earlier. You don't need this, as much of a huge operations team to do continuous build, continuous integration, and continuous deployment. So we believe that a reactive approach would be appropriate, especially too when you deal with like microservices too, because the way reactive works is that we're looking at data as streams, which is then kind of like versus the traditional way if you're kind of dealing with objects and all of these things. So and the thing is too with microservices in cloud native world, we're also dealing with very quick release cycles as well. So having a reactive approach, we believe too it should really help in terms of like speeding up and really the responsiveness of your application, and also scalability. If you want to scale up, it's also much easier. And if we need to recover, likewise too, it's also very more convenient, so to speak, right? Not like the older kind of traditional way. So essentially too, is concurrency without worrying about mechanics too of like threading concern. For example, your reactive systems will handle all of these capability very well. So. Okay, so now I think we are kind of back. We have about 5 minutes or so. I think so. We're back to that data pipeline use case that Fabio already demonstrated. So we already looked at it. So just now was just kind of going through the rationale behind it. But how about then Fabio and you and I, we can talk about the experience on building the pipeline, right? Yeah, and so
Indeed.
yeah, okay. So basically, yeah. And so as layout in here too, reactive stream standard enables different technologies to work together. I think that's kind of the beauty of it too. So you're not only tied to one things. But different implementations are not yet easy to get them to work together in the same process. I'm sure, yeah, Fabio took the time to develop that demo application. Maybe Fabio, you have thoughts too on working with our socket, you can share with us some more?
Sure. Yeah. So there was that legacy processor one. For instance, in it, you have to expose a reactive streams interface to the back pressured reactive stream interface to the producer, which in this case was the Kafka topic, and then expose another one on the output side to communicate with the legacy processor too. And in this case, on the source side, I had a Akka streams implementation, and on the output side, there was a RSocket implementation. And making Akka stream and RSocket work together in a unified pipeline, it sounds really easy because they both implement the reactive stream standard, but in reality, it wasn't really. Like, at least it required some work. It was not yet out of the box, this out of the box connection. It required some work, so it's relatively new technology. Particularly about RSocket, the third point of this slide is a great technology, but I found, of course, like all emerging technologies, documentation is a little lacking. There were useful examples, but again, then limited because, of course, every situation is different. And the Java implementation relies on Project Reactor. Which if you're a Spring user, you probably you will feel right at home with all that Flux and Mono abstractions. But I mean, if you don't like it particularly, you're still forced to use it. And also, finally, last point of these conclusions from me. Sometimes using HTTP with the addition of streaming semantics. For instance, Akka HTTP is a HTTP client and server that implements reactive streams, sort of built on top of HTTP, might be a faster and more efficient way to modernize your application rather than trying to use RSocket, which is sort of new and limited support. So yeah, I am a fan of RSocket. In fact, I am trying to write down in my own free time a Scala implementation of the RSocket protocol. But as all bleeding edge things, it's not as cushy and comfy as HTTP.
Yeah, exactly. Yeah, exactly. Well, thanks for sharing too, Fabio. So yeah, so I think then we have like maybe a few minutes left, right? So we kind of like to draw some conclusion from this experiment that we have done, and we actually started doing this talk in February, and so it's almost a couple months, 10 months, and so yeah. So some of the findings, right, we found, and as Fabio has shared too, say with RSocket, all these kind of new kind of shiny tool. It's still probably got it's very promising, but also still needs to be more field tested, and more work needs to be done to make it really fully kind of able to get adapted to some real world production system. I think that's what it is. Now, the thing is, what are like some of the alternatives, right, that we have kind of been talking about too? I'm wondering too, actually, there's also Eclipse project has also Vertex too. So Vertex and also the Small Rye Mutiny library too. I think they also do kind of similar type of things. And with Vertex, is itself an event bus essentially. So my understanding is that the Small Rye too is also having like Small Rye is a step up to like the RX library, the Reactive extension library. So they also have like, I think equivalent of Flux and Mono, they actually have Uni and Multi. I think it's kind of like the same concept. Yeah. And how about Fabio? Did you find out anything else?
Yeah, I would say, I think we are 1 minute over time. So for those interested in talking about these things, how about we move to spatial chat? That's going to be a lot of fun and also a little more interactive.
Sure. Yeah. Okay.
Yeah.
All right, then. I think then.
So I summon Erica. Eric is back.
I'm back.
Yeah.
Back, everybody.
Okay, thank you.
Cool. Well, thank you so much for that presentation. I really appreciate there's a lot of material to get through there, and I appreciate that you were able to get through it so quickly.